Hello, welcome to the another video on VLSI design course. In this video, we are going to discuss MOS transistor theory. The MOS transistor theory, the contents related to this has been divided into the following uh, topics. First, we are going to focus on the introductory topic, wherein which we are going to cover how exactly the MOSFET can be operated in different modes. The next one is going to be long channel current voltage characteristics. So there we are going to derive current voltage relationship and also show and demonstrate current voltage characteristics. And in the section 2.4, we are going to focus on the non-ideal current voltage effects. Lastly, we are going to cover the transfer characteristics, specifically the inverter transfer characteristics, and which we call as DC transfer characteristics. So these are the topics that falls under the heading MOS transistor theory. Now let us commence the MOS transistor theory introductory topic. So as we all know that MOS transistor is the foundation for any electronic system. So without MOS transistors, we cannot design or we cannot develop any electronic systems. 99.99% most of the electronic system consists of MOSFET as the fundamental element. Okay, so let us try to understand the background and the working principle of MOSFETs with its characteristics. So in chapter 1, we have seen that the metal oxide semiconductor transistor, where its role was as an ideal switch. That was our emphasis in the chapter 1. And in this particular chapter, we are going to focus on the operation of MOSFET, followed by the characteristics and switch behavior of the MOS transistors. Now let us see that what are the factors that affects the performance of a MOS transistor. The performance of a MOS transistor, or performance and power considerations mainly, they depend on the several factors. The crucial factor affecting the chip performance and the power consumptions are as follows. The two primary determinants are which affects the performance of a chip performance is one is the current within the MOSFET. So the amount of charge carriers moving through the transistor that influence the switching speed of a transistor and hence the power dissipation. This is the primary factor which is important to be considered while designing the MOSFET transistor. The second factor is also an important one, which is the capacitance. The capacitance of the transistor, because transistor comprises various layers, starting from the substrate layer, diffusion layer, metal layer, polysilicon layer, and so on and so forth. All this layer capacitance plays a very important role in deciding the performance of the transistor. And also the wires. The wires also play a significant role in deciding the performance of the transistors. So in electronic systems, there is a need to connect one transistor to another transistor. Therefore, we need to use a wires to connect the two or more transistors. So the capacitance of wires also plays a significant role in deciding the performance of the MOSFET and hence the chip design performance. So now let us focus on the objective of this chapter. In this chapter, we are going to do deeper analysis of characteristics of the MOS transistors. That's conducted here, and the focus will be shifting from ideal switch behavior to real world performance factors. That is the second objective. And the third objective is to understand the transistor characteristics, basically in order to optimize the circuit design and also energy efficiency, keeping these two as goals. So the transistor characteristics is discussed. Now before moving to the details of that, let us look at the MOS transistor symbols that are commonly used or widely used. In figure 2.1 will illustrate several MOS symbols and representation of the MOS transistors. Generally, MOS is represented with the three terminals that is shown in figure 2.1a, and that is the main symbol used in various circuit schematics. The symbols are as follows. The first one is going to be a three-terminal symbol, as we can see here. This is the first row represents NMOS symbols. These are the NMOS transistor symbols, and this second row represents PMOS transistor symbols. And the first symbol specifically, this is used in circuit schematics. These are symbols which are used in circuit schematics. Okay, and the second column, in which we show both NMOS and PMOS symbols in a detailed way. So these are called as a detailed symbol or detailed representation. And the third column, the symbols of NMOS and the PMOS that are shown are the less commonly used symbols. Okay, they're not commonly used. These are the symbols that are not commonly used. Okay, so these are the three different category we have with reference to the NMOS and the PMOS transistor symbols. Let us look into the PMOS transistor symbol. In order to understand how we arrived at this particular symbol, let us go and see the structure of a transistor. The physical structure of a transistor is as follows. This is the NMOS transistor, wherein which there is a p-type body, that is the foundation for this NMOS transistor, and there is a diffused elements which you can see, structures which you can see here is N plus, and another N plus regions are diffused here, and each one of them forms a source, you can call as a source region, and other diffused N plus can be called as drain region. And connecting this source and the drain region, there is a layer which is deposited here. The one which you see in the light blue color is going to be the silicon dioxide, which we call as a gate oxide, and the top of that there is a polysilicon. This shaded portion is polysilicon, which is a metal used to make used as a control terminal for the MOSFET. And here we can connect source terminal. This is going to be the drain terminal, source, and here we extract from the third terminal, which you can call as a gate terminal. As we can see here, this looks like a structure like, we have a drain source region, and we have we have a source region followed by a gate region, and then we have a drain region. And these two regions here, in order to show the silicon dioxide, we leave an empty space here and attach gate terminals. So we have a gate, as you are seeing here, and we have a source region. This is complete region is the source region, and we have a drain region here. This complete region is a drain region, as you are seeing here in the structure. And here this region is below silicon dioxide. Okay, and in between these two lines, you can call this as silicon dioxide, SiO2. That is the empty space between the two lines. Here you can see this portion, what I'm showing. The empty space that I'm showing here is nothing but corresponds to this between these two lines. Okay, this is a polysilicon layer. This is a line. Single line is nothing but it is a polysilicon. So this is a metal layer which acts like a conductor, metal. So in this way the symbol has been, we have arrived at the final NMOS transistor symbol. Okay, so now let us go back to the symbol here. So you can see here it is written in a vertical manner, but here we have shown in a horizontal way how we can derive symbol from the MOSFET structure. This is a 3D structure of a MOSFET, NMOS transistor. So the same thing here. So here we have a gate and source. We have upper one is going to be the drain. The empty space here, that is nothing but silicon dioxide, and this plate that I've shown is nothing but a metal, or here we can call as polysilicon. So this is the three-terminal symbol, okay, which is widely used in circuit schematics. Okay, so now you can see in the PMOS transistor, we have same symbolic representation of even PMOS transistor. The only difference between the NMOS and PMOS transistor is we have a bubble here that shows a complement. So here we have a bubble for a PMOS symbol. Here we don't have any bubble for NMOS symbol. Okay, rest all the the symbolic representation of NMOS and the PMOS remains same, except that there is a bubble for the PMOS representation. Okay, let's move on to the next version of the symbols. As it was mentioned that this is a 4-terminal transistor symbol, and this is a detailed representation of the NMOS transistor symbol. The arrow mark here shows that the electrons are moving beneath the silicon dioxide. This is a empty space, as we already mentioned here. It is silicon dioxide, and this arrow mark shows that electrons are moving to the below the silicon dioxide interface, and the rest all things remain same as the original symbol that we have shown here. We have a gate, and we have a source here and a drain, and the third one is nothing but it is the substrate or bulk terminal. Let us show this as a B. B means it is the bulk or substrate terminal. So this can be called as a bulk, or we can call this as substrate. So this is the foundation material for the transistor. Okay, so that is the 4th terminal that is shown for the transistor. So this is the 4-terminal symbolic representation of an NMOS transistor. Arrow mark is inward, that shows the electron are moving below the silicon dioxide. So electron cannot cross the silicon dioxide. Therefore, it's showing that electrons are moving towards below the silicon dioxide to form a channel here. So that is the representation of the 4-terminal transistor symbol. And for the PMOS, the only difference, as I told you here in this case we have a bubble, but here in this case we have an arrow mark going out. So here we have an arrow mark which is incoming. So that shows that electrons are moving here, but in this case electrons are moving away, and that is shown with an arrow mark going out here. That is the detailed representation of the PMOS transistor symbol. And in this case, you can see that arrow mark is placed on the drain terminal here, or sorry, it is in this case it is going to be the source terminal, and here we have a drain terminal. Arrow mark is placed on the drain terminal, which is outgoing arrow mark, and in this PMOS transistor, arrow mark is placed again on the drain terminal here. This is a drain, and this is going to be the source in this case. So arrow mark is placed on the drain terminal, which is incoming arrow mark that is shown here. So these are the different MOS transistor symbols widely used. Among these the 3 different levels of representation, the first circuit schematic version of transistor symbols are widely used compared to the detailed representation, and the last one which is not commonly used. Okay, this is about the transistor symbols, and the explanation has been given here. Okay, now let us go to the more details of this MOSFET transistor. MOS transistor is basically majority carrier device. Like BJT is both type of charge carriers exist here. Both electrons and holes are responsible for the current flow in case of bipolar junction transistor. Whereas here in MOSFET or MOS transistor, it's a majority carrier device. Either electrons in case of NMOS are responsible for the current flow, or in case of PMOS, the holes are responsible for the current flow. It's a majority carrier device, not like a bipolar device, just like electrons and holes in case of BJT. The MOS transistor operates as a majority carrier device, meaning that current in the conducting channel, that is between the source and the drain, the charge carrier's movement from the source and the drain is completely controlled by the voltage that is applied to the gate terminal. So gate terminal serves as a control, and therefore using the gate terminal, the charge movement from the source to drain or current movement from the drain to source can be made minimum, or it can be varied depending on the voltage that we apply at the gate terminal. So gate is going to be work like an control terminal. So that's how the MOSFET MOS transistor operates. And now let us look at NMOS transistor. We have 2 types of MOS transistors. NMOS also can be called as N-channel metal oxide semiconductor field effect transistor. Okay, so In this NMOS transistor, the majority carriers are the electrons. So electrons are responsible for the current flow in the NMOS transistor. More the electron, more current flow exists, and lesser the electrons, less current flow will be there in the NMOS transistor. Similarly, in the PMOS transistor, the majority carriers are holes. So holes are responsible for the current flow in the PMOS transistor. Once again, here more the holes here, more current flow exists. Okay, so I will be increased, and as number of holes decreases, in accordance with that, current also decreases. That's how the NMOS and the PMOS transistor operates. Now let us try to demonstrate the MOS structure, and let us see that what are the modes which we can operate the MOS transistor. The behavior of the MOS transistor, it can be understood by analyzing the isolated structure. And let us explain what do we mean by isolated structure. The isolated structure contains only a gate and body without even considering the source and drain. For the time being, we assume that the isolated structure is considered to demonstrate the MOS structure. What do you mean by isolated structure? Isolated structure means here we only retain the gate region consisting of the gate and the body, whereas for time being we ignore, or we don't consider the source and drain regions to demonstrate the working principle of the MOS. Okay, MOS is basically works on the principle of a capacitor. We already know how capacitor works from our the basic understanding. The capacitor means it is a device which is made up of two plates separated by the dielectric here, that is the capacitor. Okay, so we have a dielectric here which is separating the two plates, two parallel plates here, and the one plate, if we supply with positive charge, the other plate will get induced with a negative charge here. The same principle even the MOSFET also operates, and we are going to demonstrate that using a couple of diagrams here. So in figure 2.2, so which depicts the simple MOS structure with the following key layers. It has got a gate. The gate is going to be the conductive layer. Early transistor used a metal as a gate to form a gate. Later, and that it was replaced by the polysilicon or crystalline polysilicon. That was the gate material. And followed by this, we have a gate oxide, a thin insulating layer, which is nothing but silicon dioxide. And this prevents the current flow between the gate and the body. And that is called as a gate oxide. So that is the second layer in the MOSFET. Third layer is going to be the body. Body is nothing but the foundation. The bottom doped silicon layer. Generally, for NMOS transistor, the body will be of the P type, and for PMOS transistor, body will be of the N type. So here, majority charge carriers in case of P type are going to be the holes. That serves as a body for the NMOS transistor. Okay. So here we are considering NMOS transistor. Therefore, the body for the NMOS transistor is going to be of P type here. The next one is going to be the electrical behavior. The body is typically grounded. In most of the transistors, we ground the bulk or body, and the voltage is applied to the gate. And due to the insulating properties of the gate oxide, almost no current flows from gate to the body because of the silicon dioxide, which acts as an insulator. It's a good insulator and it's a perfect insulator. Therefore, there will be no current flow from the gate to the body. Okay, even though there may be, practically if you observe it, there may be some leakage current, say for example nano ampere or picoampere of current, but that's going to be very small in case of the MOSFET. Let us look at the figure with reference to the 2.2a. So here we have three different modes of operation of a MOSFET. So here, as it was already mentioned, that this is the isolated structure. So in the entire MOSFET that you have seen here, so this portion was not shown. This portion, I'll show it in the different color. So this portion is removed and this portion is removed, and only the portion that is shown is this one. So this portion is shown here. Okay, so we'll go back now and you can see that portion here. So here we have just the gate. I'll try to zoom it a little bit for your reference. You can see here, this is the isolated gate structure, and here we have three layers here. The upper one you can see here, this particular layer, this layer here. So this layer is going to be the polysilicon. This is the polysilicon layer. Okay, so this is the polysilicon gate that forms the gate, and below that we have a thin layer which is nothing but silicon dioxide, that is a best insulator. And the bottom we have a p-type body. Since we are considering NMOS transistor, the body is going to be of the p-type, and body you can see here, it is made up of only the its majority carriers are going to be the holes, so you can see the holes are residing here. Okay, so this is the isolated gate region based transistor that we are using to demonstrate the MOS structure. And here first one is going to be an accumulation mode. Accumulation. We have three modes here. The first one is going to be the accumulation mode, and the second one is going to be the depletion mode. This is depletion mode, and the third one is going to be the inversion mode. So MOSFET can be operated in three different modes: accumulation, depletion, and inversion. Okay, so to demonstrate the MOS structure, we have categorized the MOSFET depending on the voltage applied into three different modes. The accumulation mode. Let us first discuss the accumulation mode and look at the voltage that we apply at the gate terminal here. So we have a voltage source connected between the gate and the body or bulk. So the voltage source now, it is VG is less than 0. The voltage applied to the gate is less than 0. So that means it can be minus 0.5 or minus 1 volt. That is the typical value voltage that we apply here. And what will happen during this, okay, when the negative voltage or gate voltage which is applied is less than 0. So here you can see that the upper plate, which is nothing but the polysilicon gate, is now supplied with the negative charges. As you can see the negative charges here. So we have a negative charge here, and this complete region forms a capacitor. As I already mentioned here, this upper poly gate forms the upper plate, and below we have which is a p-type body. This is the p-type body that forms the lower plate of the capacitor, and upper plate is nothing but which is the polysilicon poly gate. Okay, so we have an upper is the poly gate and lower is going to be the p-type body, and by applying the gate voltage less than 0, we are supplying the upper plate with negative charges here. So same charges you are seeing here, negative charges, and because of the insulator in between these two plates, we have an silicon dioxide which is the perfect insulator, and below you can see it, since it is a p-type body, the complete body is now have a majority charge carriers as the holes, and now the holes cannot move to the upper polysilicon gate because of the insulator in between these two layers. So therefore the holes have been accumulated below the silicon dioxide, beneath of silicon dioxide, and therefore the name is called as accumulation mode. As we applied is going to be the negative voltage, and for negative voltage positive charges have been accumulated below silicon dioxide, surface here. As you can see, more number of charges has been accumulated here. So therefore this mode of operation is called as accumulation mode. Okay, and this mode is of no use for the NMOS transistor. Only thing is the charges have been accumulated here, and either side, as I told you, there is a source region here and there is a drain region here. This side we have a drain region here and there is a source region to this side, and the current both are of n type here. So the region, because of the positive charges here, these two regions remains as isolated. So current flow cannot happen through this. So that's going to be the accumulation mode. And let us go to the next mode here. In the next mode, let us see the voltage that we apply. Here voltage is slightly positive, not a negative, just like in the accumulation mode. So VG is going to be greater than 0, but it is less than the threshold voltage. Let's assume that the typical threshold voltage is 1 volt. And VG is greater than 0 but less than 1 volt. Let's assume that VG applied is going to be 0.5 volts. Now we are going to supply a gate terminal with positive voltage, as you are seeing here, positive voltage here. And observe here what happened below the silicon dioxide because of the capacitance effect here. So whatever the charges you have seen earlier below the silicon dioxide, we have seen the positive charges have been accumulated here because of upper plate has been supplied with negative charges, but in the in the second mode, which is nothing but depletion mode that we have shown here. So in this case, as we can see, so the positive charges have been given to the polysilicon gate, and therefore below we can see the repulsion, because the positive charges in the upper plate repelled all the positive charges below silicon dioxide, and therefore we see a depleted region here. And so this region is called as a depletion region here. This complete empty space that is shown here, called as a depletion region below silicon dioxide. There is no charge carriers here. All charge carriers has been pushed downward here, okay, because of a small positive voltage that is applied here, okay, that pushed all positive charges below silicon dioxide because of the upper plate polysilicon gate has positive charges that repelled the positive charges below the silicon dioxide. And this mode of operation is called the depletion mode. In depletion mode, we apply very small positive voltage to the gate. And let us see the effect when we apply large positive voltage to the gate. When we apply large positive voltage to the gate, we know that we assumed already the threshold voltage is going to be the 1 volt. And if you apply the gate terminal a greater than a threshold voltage, say for example, the 3 volts, that is the voltage that we apply to the gate. And now upper plate has now a substantial amount of positive charges, and because of positive charges has been increased in the polysilicon gate. Below we can see that here all positive charges that were here pushed downwards in the, as in case of the depletion mode. But now since the a large positive voltage is applied to the polysilicon gate, we can see that the silicon the minority carriers in the p-type body, there were electrons, and all these minority carriers has been now occupied the region below the silicon dioxide. This thin layer, which is a line here that is shown, is nothing but the silicon dioxide. Below silicon dioxide, we can see that is charges, negative charges have been accumulated here. Okay, so here we can call this as an inversion region, because the complete body is of p-type, and because of large positive voltage that is applied to the gate has inverted this p-type, and it has made as an n-type here because of the charges induced here. This complete region has become now, it has changed from earlier it was a p-type, okay, below the silicon dioxide. Now because of increased voltage at the gate, gate point, gate voltage, the p-type has become now n-type. So this p to n conversion is an opposite. That's why the name is called as an inversion region. And below that you can see that there is empty space again here that forms a depletion region here. And now we can call this inversion region formation layer as it looks like a path for the charges to move from source to drain, and therefore this a layer of electrons present below the silicon dioxide can be called as channel. So the important the parameter in order to understand the MOSFET, channel has been induced here because of the positive voltage applied to the gate, and we call this as an induced channel because of the capacitance effect that is happening within the 3 layers that has been shown here: the metal, silicon dioxide, and the p-type body. And due to the large voltage applied to the gate, the below silicon dioxide, a complete p-type here below silicon dioxide has become an n-type here. Therefore the region is called as inversion region. And here the source carriers from the source can move if you apply suitable potential between drain and source. Now charge carriers can move from source to the drain region via this channel, and current conduction can take place here. That's how the MOSFET works. I hope with this 3 modes that we have shown here, the one is accumulation mode, where we apply the negative voltage to the gate, and charges have been accumulated below the silicon dioxide. And in the second case, we apply a positive voltage, but a small positive voltage. We don't apply a large positive voltage, small positive voltage that is applied here, that made the all positive charges to repel below silicon dioxide, and that created a depletion region, and this mode is called depletion region. Whereas here, when large positive voltage is applied beyond the threshold voltage, then this voltage is sufficient to convert p-type body below silicon dioxide into the n-type, and that region is called as a channel. And this channel helps us for the charge carrier to move from source region to drain region, provided if you apply drain to source voltage. And there's again depletion region created below the negative charges, and this mode of operation is called as an inversion mode. Okay, so all these things have been explained here, so students can go through this, and if there are any questions you can post it in the comment. So this is what the three modes of operation. It is important to understand the MOSFET phenomenon, and the voltage that repels from holes from body and attracts free electrons, forming a conduction layer, which already seen, that is called as a channel. The threshold voltage is an important factor, so to be understood. We'll deal that with the mathematical equation in the upcoming classes. The threshold voltage depends on several factors, like for example, it depends on the doping concentration and also depends on the oxide thickness. Varying the dopant concentration or doping concentration and oxide thickness also changes the threshold voltage here. Vt is usually positive for the NMOS transistor, whereas it is negative for the PMOS transistor. So with that, we have come to an end of this demonstration of MOS transistors. We have discussed three modes of operation, and we also discussed MOS symbols here. And in the next video, we'll explain the working of MOS transistor. Thank you all for watching this video.